Hi everyone, welcome along to this, my second live stream on electromagnetic induction. Today we're going to carry on and look in a bit more detail at the difference between B, phi and N phi. We'll jump into Faraday's law and then use what we've learned to look in a bit more detail at what happens if you have a solenoid and a single coil and then you try and induce an EMF in the second using DC or AC in the solenoid. I find that students get quite confused about that because it's difficult. So let's jump straight in then. We'll start off by considering a little bit of what we did last week. So electromagnetic induction is fundamentally when you have a wire and you move it through a magnetic field like so, and then you can use your Fleming's left-hand rule to work out that this electron is going to feel a force to the front. Now, if you want a bit more detail on that, then check out my first live stream where I explain that more fully. The net result of this movement, though, or this changing in the flux that's cutting down through the wire, is that we generate an EMF between the end. And that's the basis of everything we're going to do today. So a change in flux in that wire there. Flux being a word that's used to describe the lines. So let's continue. We're going to spend a moment just looking at what is the difference between these three terms. Really importantly, so you can think of B as being magnetic flux density. You'll see why in a mo. Phi, that's the Greek letter phi, is called magnetic flux. Very similar, isn't it? Whereas N phi is magnetic flux linkage. So I'm going to actually write the full word linkage or linked in there. So let's unpack each of these then. So first of all, let's look at B. B is, I like to think, relatively straightforward. But what's going on here is we have to consider a coil. Now, these coils are complex. So I'm going to just spend a minute on this. If you imagine a lollipop stick, what you have is this like a little wooden square, the lolly stick. And then we stick another one like this. Now, I'm not drawing the curves. So now we have two pieces. Here's a third lolly stick, like that, and then the fourth one. So we've stuck them together into a kind of a hole, or a square hole if you like, and we can stick our fingers if we wanted to kind of through that center point. Now this combination of sticks, as it were, is known as a former, and then what you do is you get your wire and you wrap it round and round this coil, and it goes down the back where obviously you can't see it, and then across the front and then back up again. So in my coil here, I've drawn it with two turns. Now, magnetic flux linkage, B, see what I did there? It's not magnetic flux linkage, it's magnetic flux density. So the magnetic flux density is the number of lines that go through this coil. See the red lines, the flux lines there are going through the coil. Look underneath and then in front of the lollipop sticks, if you like. The number of lines that go through if that coil has an area of 1 meter. So the best way to imagine it is just simply a coil of size, square coil of size 1 meter, and then count the number of lines going through. Now it's worth just pointing out, of course, that several things. Firstly, these lines don't really exist. You can't put a magnet down on the table and look, oh look, there's the flux lines. It doesn't work like that. These are a model or a construct to help us describe what goes on with magnets. Moving on then, no coil, or very few coils in real life, are as big as 1 meter squared. So what we next do is we imagine a real coil. Most coils that you will come across in A-level physics are this kind of square shape, but in reality they're often curved. So here we have a kind of an attempt at drawing a 3D curve. Now this coil only has an area of A, so the area of this coil is smaller. That means that the flux, the magnetic flux going through that coil, is the number that you would have going through 1 meter squared by the number or the size of the actual area there. So if the area is a quarter of a meter squared, then obviously you have a quarter times B, which is the area that would go through 1 meter squared. So actually it's really straightforward. Worth pointing out though that we only have one turn here. So coils come in an absolutely gigantic range of shapes and sizes and colours. Now N phi is really straightforward. All that's happening is that instead of one turn, we have two turns, or 10 turns, or maybe 10,000 turns, n turns. So that simply means that the magnetic flux linkage is just going to be phi, magnetic flux, times the number of turns that we have. In other words, times n. Now, that means that we have BAN on the other side. I do like it when physics formulas make little words. So n phi is BAN. Now, if you're anything like me, you've been so highly trained in maths that your immediate reaction is to knock out those n's. But in this case, don't leave them, because for magnetic flux linkage, it can be really useful to have that n. But do bear in mind that these two are really the same. It's just that as we move from the bottom to this one here, all we're saying is that n equals 1. So they're really two ways of saying very similar things. Right, let's move on. Now, in the first slide, we were saying that we can create this EMF by moving a conductor through a magnetic field. In fact, it's a little more subtle than that. So here we have a nice simple diagram of a bar magnet on the right there and a coil. I've got n turns, as you can see, connected up to an ammeter. Now, if I move the magnet towards the coil like this, you can see that the flux going through that coil has changed. Here, if we continue these lines on, so obviously this straight one is going to go through the middle, that one might just go through it, and perhaps that one too, but these ones are clearly going to miss. As I bring the magnet nearer to the coil, so more lines of flux are going through the center. In other words, the flux has gone up. That change of magnetic flux in that coil will induce an EMF and hence a current. And of course I can do the same thing by pulling the magnet out, because now we're going to decrease the number of flux lines. Again, we'll get a current. But it's worth pointing out, of course, that you don't have to move the magnet. You can move the coil, because that coil is now still experiencing a change in the flux that's linked through it. So in other words, it doesn't matter what you move. So I think one of the textbooks talk about you can waggle your coil in front of the magnet, or you can waggle your magnet in front of the coil. It doesn't matter, same effect. Flux lines are changing. Sometimes the textbooks will talk about flux lines cut. And that's a helpful way to look at it too. But again, it's not the only way. And there are some issues with that. Okay, so moving on, we're about now to come to what is really, along with Lenz's law, perhaps the most important part of this topic. But first of all, a very short maths detour. You will very often see this in maths, a change over a change in time. So for example, this could be change in voltage, it could be change in mass, it could be change in acceleration, length, anything you want as a change. So what we have here is a change over a change in time. And this is so common in physics that we call this the rate of change. And then we would say I'm going to put x, where x is whatever we've written up there. So get used to this. This is telling you how much something changes in 1 second. Normally a second. I mean, I suppose delta t could be years, couldn't it? If you're looking, say, at, I don't know, the brightness of a star as it begins to give out light. That's going to change over years. But normally, for us, it's going to be a second. So rate of change. And again, you'll often see that written in maths as d over dt. Again, if you're not really a maths person, you don't need to worry too much about that. And this leads us to Faraday's law, which is a really great law. I enjoy this one because I'm a nerd, I suppose. So here you can see we have rate of change. Now, n times phi, you might think to yourself, well, hold on a minute. He's taken n and phi and split them with the change. Now that's okay, because this can be written as EMF is proportional to delta n phi. Now the thing is, from a mathematical perspective, because n, the number of turns, is a constant, we can just as well write it out the front. So don't get put off by that. What we're seeing here is the rate of change of n phi, which is flux linkage. So Faraday's law is telling us, notice this isn't an equals, it's a proportional, that the EMF induced is proportional to the rate of change of flux linkage. Now, this is so important. So, I kind of joke, especially with my AQA students, that really the only thing you need to know in this topic, every question, you just pull out Faraday's law and you say to yourself, is there a rate of change of flux? And that will lead you towards the EMF. And so from that formula, from this simple formula, you're able to build up all the things that are happening, because you can now explain why is it that if I move this coil slowly, I only get a small current, whereas if I move it fast, I get a bigger current. And of course, that's to do with the rate of change of flux. So maybe consider this as another example, if I can do it. In actual fact, yes, I can. So what I'm going to do is just turn this magnet round, make it a little bit smaller like that. Now take the coil, turn that round. I'm afraid the A's gone upside down, but let's not worry too much about that. And then we're going to drop that magnet. Okay, we're going to drop it. Now, as I'm sure you know, as you drop something, it accelerates. In other words, it starts moving faster. Now, we also know that the EMF is proportional to N change of flux linkage over delta T. So this is quite a really interesting question. What do you think is going to happen as this magnet falls? Well, it's speeding up, isn't it? So as it moves towards the coil at first, you can see that the rate of change of flux is increasing. In other words, it's getting bigger, but it's getting bigger more quickly. And the reason for that is if we kept it moving at a steady speed, then the number of lines going through the coil is increasing. So we get an EMF. But the fact is the magnet's accelerating as well. So not only are we getting more lines, but they're coming more quickly. So in other words, you get a real big EMF. And then as the magnet comes out through the bottom of the coil, like this, then obviously the magnet is moving faster than when it approached. So we get a really quick or a really large rate of change of flux, meaning that we're going to get a bigger EMF. So what you find, in fact, is that as the magnet comes towards the coil, you get an EMF. And then as it comes out the end, you also get an EMF, but a bigger one. But what happens when it's exactly in the middle? What happens when it's in the middle? Now, at that point, as I'm sure you know, these flux lines, they curve in circles. And as I'm going to have to move the magnet now, otherwise I'll destroy the diagram. But there is a section, imagine the magnet falling along with those lines, when there is no flux change, because you are pulling the magnet through the straight part of the field like this. In other words, the magnet's falling kind of parallel to the field lines, and so there is no change of flux just for an instant in the middle. So what you find is in the middle position there is no EMF induced. So this is a real great question, because what you end up with is, if this is time and this is EMF, as the magnet first moves in, you get something like a spike like this happening. So this is the point where the flux is changing really quickly, and then we get a middle section where the magnet's going through, rather like I've drawn it now, where there is no rate of change of flux. And then the coil comes out the other end, but it's moving faster. So that means that the peak is not only bigger, but it's also thinner, because the whole thing's coming out quicker. And it's also negative, because we were building the flux up and now we're decreasing the flux. So you get a really interesting, a couple of spikes here with a flat bit in the middle. Right, well, let's get into the next bit that you might consider to be like the last bit of this topic. So, or for this section today, I want us to imagine what happens in a coil. So you see we've got a single coil, a coil with multiple turns here, and we've got a solenoid. Now you know that at the moment the switch is open, so there's no magnetic field, so we can do our wiggling with whatever we want. There'll be no current or no EMF induced. So let's close the switch. What we're going to do is close the switch, wait for a second or two, and then we're going to see that we have some flux lines coming out like this. Now, what will we see on the ammeter? Will we see a reading? Will there be an EMF? Well, if you don't know, and why would you, reach for the formula, as always with this topic, Faraday's law, and say to yourself, is there flux changing? Well, after the switch here is closed, it's been closed for say a second or two, the flux lines have settled down, he says, adding a few more. In other words, the coil is having flux lines go through it that aren't changing. And so a DC current in this coil produces a constant magnetic field or a constant N phi, and consequently we get no EMF. But as with all things, it's more complicated than that. What happens just before, so I just need to move, blimey, stupid thing. Ah! Yeah, sorry about that. A slight annoyance trying to remove a line. So I was just going to say what happens at the instant that you close that switch. Well, think about the current in the coil. Let's say when the switch is closed, we'll just make a number up, 1 amp. But when the switch is open, it's 0 amps. So in other words, the current in the coil of the solenoid goes from 0 to 1. And that happens, as you might imagine, really quite quickly. So the current with time inside the solenoid will do something like this. This is the point where you switch it on. It's going to build up rapidly and it's going to settle down. Now the magnetic flux coming out from the solenoid kind of depends on the current. So at this point we're going to get quite a large magnetic flux, but it's constant. And at this point we're going to get no magnetic flux, which is also constant. But as it moves up the turn where the current is increasing, so will the lines. The number of lines there will increase quite dramatically at that point. So what this means is that as you click the switch, you will get an EMF, and I'm ignoring the sign for those of you that might be thinking about it. But what you'll get is an EMF that is nothing up to this point, nothing again after that point, and in that point you get a spike. And you get a spike because there's a rapidly changing EMF in there. Okay, so you can get an EMF with DC, but only when you change it on to off or off to on. All right, what about with an AC coil like this? Now this is interesting too, because as you know, for AC, if we were to sketch the current for an AC, well, I've already kind of drawn that wrong already, haven't I? It should go like this. So here's time, here's current. Now it follows a kind of a sine wave or a cosine wave, depending on how you want to think about it. But the point being here is that the current is, and the phrase they like, constantly changing. It never settles down. It's either going up or it's going down. So what's happening is the current is going first one way. It's building up its strength, if you like. It's getting bigger. It reaches a maximum. It decreases, reaches the middle point, swaps over and starts going the other way. So it's sloshing backwards and forwards, different speeds, different directions. That means that the magnetic field created by the solenoid is also constantly changing. I've got a rather nice little animation video which you can go and look at. It's only a short. I'll leave the link below. But what it tries to show, this animation, is something like this. So at the point where there is no current, i.e. where that circle is, or this circle, or that circle, no current clearly means no magnetic field. At the tops of the curve, we might have a whole bunch of field lines. Let's put some field lines in, all going this way. In other words, that's a north. As we travel back down the curve, so these field lines will become less dense. They'll move away from each other, but they're still pointing north, getting less and less strong. And then you reach the point back at the 0 where we cross over our axis, here again, back here, where there's no field. And now the field lines start to build up again, except this time it's not going to be a north, it's going to be a south. So the field lines are going the other way, and they'll build up and get stronger. So in other words, if we have an alternating current, that's going to lead to a constantly changing N phi, or a constantly changing excuse me, flux linkage in our coil. And as we know, EMF in the coil from Faraday's law is proportional to N, change in flux over change in time. And this bit here is constantly changing. If it's constantly changing, that means that the EMF induced in that coil will also be constantly changing, which means that the current in the ammeter there is also constantly changing. So this constantly changing is a really useful phrase for your exam answers, you know, to help you get some clarity for those lovely markers. So the point is, if you put an AC current in here, you'll get an AC current induced, or perhaps we should say an AC EMF leading to an AC current. Now, they won't necessarily be in phase. There's going to likely be a phase difference, but that's a subject for my next video. So in the next video in this series, I'm going to tackle the really difficult subject of a spinning coil inside a constant magnetic field. Beloved of the exam boards, this question. Difficult, but really good. Well, I hope that was useful. Please do feel free, you know, to drop me a line, say, hold on, you didn't explain that bit very well, or however you feel about it. Okay, so bye for now.